I'm ready. You ready? All right. Let's talk about network vulnerabilities. This is like frequently what people think about when they think about hacking, right? That the whole shebang is just attacking networks and network vulnerabilities and systems on those networks, I suppose. But it tends
Sounds about right for the common conception of it.
that and like hacking as a verb usually means to people like just breaking into computers in the interest of doing evil,
Yes.
which is certainly not like what the deal is there. Right? There's more to it than just breaking into computers to do evil. So for the lay person, perhaps, this might be exactly what people think we mean when we say hacking. But it's not exactly.
Sometimes it's not evil, it's just fun.
So fundamentally, what can get you into trouble is like learning system hacking might leave you missing out on the protocols that underlie those systems. So, you know, the like TCP and Ethernet and 802.11x were all made in an era of kinder, gentler computing, and so we need to realize that that's the case, and then think pretty seriously about how we are going to, like understanding how understanding those fundamental protocols means that you like can attack those fundamental protocols. So like having a deep understanding of those is super helpful in this sort of thing. So we will talk about DOS attacks, about various forms of spoofing, about various forms of man-in-the-middle attacks, and then network services that have issues all by themselves. So for that, you've got network exploits, which of those attacks we're talking about, just about any time you've got a network protocol, if you can create enough like legitimate-ish traffic for it, you can deny service to that system. And the example I like to use for this is back in the day, there was a very popular website called slashdot.org. And back in the day, I mean like the late 90s. They were such a popular website that if your website made it, it was basically a news aggregator. If your website made it onto their news aggregation platform, you probably did not have the server infrastructure available to withstand the onslaught that you were going to get. And people would call that phenomenon being slash dotted. Like you got so much traffic all at once that your system just couldn't handle it and it got knocked offline, which is a denial of service and in fact like a distributed denial of service attack, which is no good, but like not a malicious one. So anytime you can if you can do that by hook or by crook, by software or a tool like the low orbit ion cannon, you create a denial of service condition. Maybe attack's not fair. So if you can focus on the protocols, you can slip past authentication controls. You can slip past potentially controls in place to protect data, or you can use that as sort of either a distraction from or a thing to use in tandem with another attack. There's a bunch of different protocols that we'll look at that talk about how to resolve names from one to another, DNS being the biggie for resolving names to IP addresses on the internet. But there's also ARP is a resolver in a sense down here on layer 2 that resolves MAC addresses to IP addresses. Potentially you can use other layer 2 problems to blip across the network using like VLANs as a way to slip through things. And then there are issues with network access control that should be a concern to you, potentially letting you slip past like a restricted LAN or something like that. 802.1x type defensive protocols. And finally, like man in the middle or on path attacks let you either sometimes take control of a conversation on a network, or they give you the ability to at least see the conversation on the network. There's no magic bullet to get you inside of encryption, but it will let you see the volume of traffic going across the wire and back and forth. So denial of service is pretty straightforward. You create some sort of volume of traffic. Potentially you can do that by crafting strange packets and sending them across the network. So way back in the day, there was this thing called a ping of death. That was like a big deal for like the 1990s IRC wars. It was a big deal, and if you sent a carefully crafted packet, the network protocol that would be responsible for listening to it would blow up on you, and the Windows TCP/IP stack would fail. So the end result was, if there was somebody being mean on IRC and you used the ping of death tool to send them a carefully crafted packet, their computer would disconnect from the internet until restarted, and the network stack was replenished. That, like one of those old-timey things that you think has gone away, but crops back up. They found a similar vulnerability in the network stack on Windows machines for IPv6. So if you sent a carefully crafted IPv6 packet to a Windows box, you could knock them off the internet again. So it was back. That's on the protocol layer. On the application layer, if a protocol like HTTP, which is an application layer protocol, or another one of those has flaws, I think the last big one was maybe like Heartbleed was huge. It affected a bunch of web servers. That would cause the malfunction you really want, which was you would be able to read random memory right out of the brain of the system, which is kind of a big deal. So application layer flaws can turn into a pretty easy denial of service attack. If you think of WordPress as an application, all kinds of flaws exist inside of it, potentially crashing the server, and even scarier, like most bugs start off as some kind of, if you do this, the system crashes. But usually what happens is you get a really specific type of doing this, and you find that now you can cause code to execute remotely or stuff like that, or data memory leaks out, or some other very bad thing happens when that shows up. So these are a list of different denial of services types. A simple ping flood works as long as the attackers have more bandwidth than the attackees. So popular on systems where, like if you've got the Mirai botnet at your disposal, it doesn't really matter what type of attack you use. If you're attacking somebody with, if your network connection is only good for, 100 megabytes of megabits per second of bandwidth, and you get attacked by 101, this looks more like 200, maybe 600 of traffic, you simply no longer can connect to the internet. So anything that will exceed the amount of traffic that or bandwidth rather, that you have available, basically can be a denial of service attack just by the function of the internet. So I always think of Brian Krebs getting attacked by the Mirai botnet, where they just basically knocked his site offline by flooding it with traffic. He did get help from Akamai, who stood up, more servers that eventually exceeded the amount of the DOS attack by having a bunch of clones of his site essentially come up on different parts of the internet and overwhelm it. So some of these attacks are a little old. Smurf attacks and ping of death and teardrop attacks and well, sin floods are still a thing. But we're taking advantage of specific flaws inside of usually the Windows IP stack, which might not have been the WinSock stack, might not have been the best written piece of software known to mankind. Sin floods, if you recall your networking fundamentals, you've got the three-way handshake, and the first part of that handshake is saying, hey, we would like to synchronize with you. I just had Wireshark open, so I have that first packet available to take a peek at here. Let's look at the ultimate PCAP. But you'd start any TCP session with one of these SYN packets. And if I just send you SYN packet after SYN packet after SYN packet, the request is, hey, let's synchronize. And if there's no one to synchronize with, or if I never send that next packet, again, poorly written TCP stacks would sit there and wait. Right? They would wait for that SYNAC. They'd send that SYNAC and they'd wait for the final response, and they'd just never come. So it was a sort of easier way to take advantage of the protocol in order to flood things down. NTP amplification, actually there's a number of amplification attacks out there. And the idea being you've got, NTP is a good example of this, but there are a lot of protocols that have this property. So if I'm trying to knock Tyler off the internet, but I only have my limited bandwidth, this is me, and this is Tyler. A poorly configured NTP server, or many of them, when sent a response, or a request rather, and since NTP can run over UDP, I think that's true, will respond back with more bandwidth than I sent over. And so sometimes those amplification attacks are measured in how much they multiply the attack. So if I send over 1 byte, I get back 10 bytes. And if, lowercase b, and no, uppercase b. And if I do that enough, I manage to amplify my attack by virtue of those systems having a protocol that doesn't really check too well who it's talking to, and B, returning more response than it sends. DNS is guilty of this sometimes as well. Certain DNS implementations would take a packet, and I guess you can spoof the return address of just about anything, although you don't do the SYN-SYNAC stand-up with UDP. So any of those protocols that will let you send a request that's not particularly well honed and get all kinds of responses back are vulnerable to those amplification type attacks. And then flooding is your run-of-the-mill, we send more traffic than you can handle. Again, how you do that's the technical details that need to be worked out in the engineering of an attack. And then any attack that is designed not to be noticed and not to be recognized, we'll call low and slow. So them's a bunch of attacks you can do on the network. One of the nice things about TCP is that it makes it harder to do address spoofing, since it asks you to set up that SYN-ACK business, although not impossible. If you're looking at MAC address filters on a wireless network, if you've got a wireless network where only certain addresses are whitelisted, if you've got an adversary who's attacking your network, it's not going to be that difficult for them to spoof that address by setting up their software to say, my MAC address is the same as the address of this legitimately connecting system on the network. So it won't take too long if you're sitting there with a wireless network attack device, like a Kali box with a good Wi-Fi adapter that allows you to do promiscuous things on it, or a wire or a Wi-Fi pineapple or something that we'll look at a little bit later. Those things will let you get in trouble. Usually your MAC address is just a matter of going into your network card's properties and saying, I would like it to be this address. Although you can get you in trouble if you start wandering around like other people's wireless networks with IP network MAC addresses that are things like dead beef or bad, bad, bad. Although fun. You got to keep the people who's reviewing those logs, you got to keep their lives a little spicy. So changing your IP address to the host you're impersonating is, like, if you can get away with that, is of limited utility. So if you, the trick is that like the rest of the network has to acknowledge that that's the appropriate address. So if I set my network card's address to Google, nobody else cares, right? Because I'm not in the routing tables as Google. But on a local area network, that's a different story. And then in most operating systems, configuring your network address in all operating systems to use promiscuous mode, which means that it will listen to packets not destined for its MAC address. So normally when a network adapter is behaving itself, the first thing it does is take a peek at the MAC address of the packet it's looking at, and if that MAC address does not equal its MAC address, it drops the packet. Setting it to promiscuous mode means that it stops that behavior and looks at all packets and essentially passes them up the stack from the network card up to the operating system. So on layer 2, we have ARP that returns the address of the systems that we're concerned with, right? The local area network is only concerned with, sort of only concerned. Layer 2 is only concerned with MAC addresses. Layer 3 is concerned with IP addresses. So on layer 2, ARP is responsible for saying this network card is equal to this MAC address. And if you, let's see, we should have ARP in here somewhere. Yep. Down here, if you see ARP protocol chatter, it looks a lot like, this tends to be the conversations that ARP have are not particularly exciting. They tend to be, who has this MAC address, please tell, or who has this IP address, please tell this IP address. They send it out as a broadcast to everybody. They get a return from, in a perfect world, they get a return from the legitimate holder of that MAC address, or of that IP address rather. But since this is an insecure protocol that doesn't have any sort of authentication built into it or anything like that, there's no way to know if that's actually what's going on. On layer 3, you've got DNS that goes through and resolves joe.com to the appropriate IP address. So here we have a DNS conversation where we're looking for webernets.net. We send a request off to dns.google.com to figure out who webernets.net is, and we get a destination back for that address. So we figure out where blog.webernets.com is, and it appears that it is at do we get a response back? Nope, just the query. Google doesn't know where webernets.com is, or we didn't see the return on that. So if you can get inside of that connection and cause shenanigans or poison the ARP or DNS cache. Anytime you cause a like in real time connection problem for these, we'll call it spoofing. When you spoof a MAC address or spoof a IP address, when you can make one of the tables that retain those lie, essentially. If you can poison the ARP table that each computer hangs on to. This is my ARP table that's got a bunch of the network connections that I'm using on it. If you can make mischief in here, you can cause all sorts of trouble, really, for systems on the network. But you can, this one would be particularly important, right? 192.168.1.1 maps to this physical address. On my network, interestingly enough, there's two addresses, two IP addresses that map to that physical network address. The reason being, one of them is a HTTP server that my router runs in order to serve up invisible pixels when I block ads with it. But if you could spoof that address, now you're doing a man-in-the-middle attack, potentially. If you can tell, the network that instead of being this MAC address, the address of the Kali machine is the MAC address, then we're off to the races. So poisoning when you do it to one of the caches, and spoofed when you're doing it in real time. So you can poison two different types of ARP caches. You can go after the switch that connects devices, or you can go after the systems themselves. The way that this is generally done is that a system creates gratuitous ARP packets on the network. So when we say gratuitous, all we mean is that nobody asked for that ARP update. That's one more than we were looking for. So they fire up, they send out ARP requests that nobody was asking for, and they get labeled as such. So if somebody sends out an ARP request that says, I have, and here's an example of a gratuitous ARP, this address here that there is no request for. So here, Cisco 1A 2B99 broadcast out, hey, I know nobody asked for 192.168.121.253, but here's the address for it anyway. And it's done it twice, in fact. So it's sending out ARP messages that nobody asked for. Now, there's legitimate reasons for doing that. Certain types of network failover technologies make use of that little quirk of the ARP protocol, but generally speaking, it should be sus. If you see that going on your networks, probably means that somebody is up to no good. So impersonating the router is a great way to do that. So if you've got a attacker who sends a ARP broadcast to this victim here and says, hey, that IP address, that's maps to my MAC address. Now whenever somebody goes to send traffic to, this is our gratuitous ARP, when they send traffic to that address, they instead go to this user. And usually the way you do this is you would have the attacker intercepting that traffic and either inspecting it, or if it's encrypted, this is a case where if you pass a certificate over to this guy and you pass a certificate over to this guy, I can pretend to be the victim to the server, and I can pretend to be the server to the victim, and I can read all of the traffic that goes on in between them. Which, super fun deal. Now all of a sudden you can do all sorts of shenanigans and malarkey. Similarly, DNS caching is when you do the same kind of trick to the DNS server for a system. So like on a large scale, usually it's a problem to do that. There was a problem on the internet called the Kaminsky attack, which was a huge problem. And I'll drop this link into the video for this, but a fella named Dan Kaminsky noticed a pretty significant vulnerability inside of DNS itself. And this was a while ago. I recommend the Great DNS Vulnerability of 2008 as a like cautionary tale about how these things are perfectly secure right until they're not. But ultimately, he found a flaw in the way the DNS worked that was essentially worldwide. So normally, this is a difficult thing. If anybody else other than a white hat security researcher had found that, the internet could have been seriously, seriously hobbled for a long time. Like you could make Google go to any IP address you wanted, and that could be a problem for somebody. On a local network, we saw like you could do ARP poisoning. You could send out a bunch of DNS garbage. You could use ARP poisoning to send out the address of the DNS server and then pretend to be the DNS server. That's one way to do it. Malware likes to compromise the hosts file on systems. So if you have a Linux system, that's the etc hosts file, which keeps a list of known hosts. It's like how the internet worked before we had DNS. You would, like way back in the early days, you would have a etc hosts file, and in that etc hosts file, you would have the list of all the host names that you wanted to map to a system. And like that may be more analogous to NetBIOS, which we're going to look at in a second here, but it was how you would figure out what system connected to what address. And like that lives on in modern systems. In Linux, in a folder called etc or etc hosts, and in Microsoft, they stuff it in Windows, System32 drivers, etc. And inside of here is a hosts file that keeps track of all of the different hosts that that system should know about. And a popular way for malware to like trick you into going to a wrong address is by using the hosts file to do that thing. So in a hosts file, you've got a mapping of IP address to DNS name that will actually override DNS. So also of interest, you've got a LAN manager hosts file for Windows. You've got the network files for systems it knows about, and then you've got a protocol file which keeps a not particularly lengthy list of the protocols that your Windows machine understands. But worth keeping an eye on that etc hosts file to know what kind of systems are on your network. Oh, and then the services file too. If you're interested in an easy way to find what port maps to what service, the commonly known ports, there is a list of them right in your C:\\Windows /System32 /drivers /etc folder. Why? Just because Microsoft let that live on. So yeah, once you can compromise DNS, you're in a pretty good spot. There's a South American banking concern that I don't know as we ever found the name of the banking concern, but they lost not their DNS, but they're registrar credentials. So the credentials you give, in my case, I use a German company to do like my game server DNS name. I use the I use roze.ma as my professional like consulting and stuff email address to manage the social media personas. And that's run out of, I think MA is Morocco. And so like somebody, if you get a hold of those registrar servers, and those are the servers that say, hey, if you're looking for the .ma domain, go to this server here. And then you ask the .ma domain, where is rose.ma? It gives you the address that's appropriate for, you know, my mail server and whatnot. But yeah, South American Banking Concern had theirs compromised and wound up with all of their addresses pointed to, they just pointed the domain name to a different DNS server, and then all of the addresses for their customer-facing website, their web app, their ATM machines were phoning home to their site. Frighteningly enough, many ATM machines to this day are basically a dumbed down Windows computer with a web browser that goes to the banking website. So when they changed the domain name, that went along. Causes lots of problems. So if you can compromise those servers or a DNS server, or if you're working on a smaller scale and you're talking about compromising a local network, if you can get into the router, you can cause all sorts of shenanigans. Similarly, DNS is one of those protocols that's like a quickest to the draw. DHCP is another one of those protocols that's like quickest to the draw. So if you send out a DHCP request, and as luck would have it, I have this handy PCAP file that's got all of these different protocols for me to look at. The DHCP protocol isn't really all that bright about how to, again, no authentication. You send out a request for, hey, I'd really like an IP address. And you get back, here's an IP address. Right? The protocol's pretty dumb. So if you do that, I realize I haven't been sharing my screen, Tyler. Is that any better resolution-wise? I guess if it's just me. You're still muted, so I can't hear your response, but.
Yeah, sorry. Because it's just the two of us, when you don't have your screen shared, your icon is still pretty big. And so
Cool. I was looking at it while I was going to read the DHCP offer here.
Yeah, some of the super fine stuff was hard to read, but well, with you reading out, it was pretty easy to run.
Cool. All right. So, but this is no security with DHCP here, right? So if you can see a DHCP request and spoof the response before the DHCP server does, the client will accept what you told it as gospel. All right, so it's saying, this is my IP address. Here's your address, Mr. Client. We know your MAC address. We know what was going on here. Oops. Which conversations did I just iterate through there? Oh, I went through all of the UDP conversations on this PCAP. This was kind of the one we want to look at, this acknowledgement here. So you get this offer, you acknowledge the offer, and now you've got an IP address. But inside of that IP address as well is all of the information about what DNS server should I be talking to. So if I set that domain name server to my evil domain name server, because you sent out a DHCP request, I respond back with my lies and damn lies. The next thing you know, I can tell you to go to whatever server I want you to go to based on that information. So yeah, that last piece there, you can modify the hosts file found in etc hosts, add your own DNS requests. That's super popular with malware. Also useful if you're doing like work in your cyber lab. Put some addresses in there and it'll override whatever the real internet tells it about those things. In Microsoft Windows, usually like Active Directory networks, you will use potentially NetBIOS for name resolution, although even Microsoft is moving towards DNS as opposed to having people lean on NetBIOS these days. But it does the same function as DNS, right? The link local multicast name resolution, the link local multicast name resolution, or LLMNR, is like DNS, but the idea is that it lets peer-to-peer systems figure out who's on the network. So if you've ever pinged the name of one of your Windows boxes and got a response back, so if I ping Daredevil and get a response back, which is questionable. Oh, because it's off. How about Silver Surfer? That's a Mac. Who's online today? How about if I ping Thor? I get a response back, and interestingly enough, I get one that's back in IPv6. Do I have a... I think she's offline too. Computer off. But if you get one of those back, it's using probably LMNR, and I wonder. Let's clear that filter. Nope, I don't have one in this PCAP. But if you turn on Windows, if you turn on Wireshark on your Windows box and record for long enough, you'll start seeing these on your network. NetBIOS was sort of the older version of that, but if this isn't working correctly, Microsoft will fall back to that. These are the ports you would be on the lookout for Windows. Notice TCP and UDP. But again, if you can lie about who Thor is, you can impersonate Thor, if that's how the system is resolving it. All right, and then if you have set up a network that involves VLANs, which are virtual LANs, which are actually packets inside of, which are actually encapsulations that wind up on Ethernet packets that say, this packet is destined for LAN 1, and this packet is destined for LAN 92. Without them, they go to the default VLAN. So if you can jump from one VLAN to the next, if the switch knows what's going on in that VLAN, you can move things around. We spend a lot of time in the Cisco classes talking about how to pull these particular stunts off, because the convenience and awesomeness of VLANs is great. You can, you know, if you've got a network where you've got the third floor, second floor, and first floor switches, they've got big backbone connections that make them perform super fast. You can have VLAN 1, 2, and 3 on each of them. And if you've got a system on VLAN 1, even though they're on different networks physically, right? They're on different wired networks. The switches will conspire to make it look to all of these hosts as though they are on the exact same network. And that's sort of the beauty of VLANs in 22nd. To make that happen, you'd need to do a bunch of stuff on the switches, including creating trunk links that allow VLANs to pass over those wires that were connecting those switches. Depending on the way the switch is set up, you may be able to make the port that the attacker is connected to see traffic for all VLANs all the time, which can be a bit much. If you're using one of the protocols that does automatic VLAN configuration for your switch and how your switch functions, which I usually advise against, you can attack those things and wind up having your switch, your attacking machine, pretend to be a switch that's supposed to get this sort of information. And then you can take advantage of switch configurations by putting a tag for more than one of the VLANs that you should be talking to into those switches. There are ways to defend yourself against those sort of things at the switch level. And if you're interested in how to do that, please see our Cisco class. We'll spend a little, actually the lab will be to use this responder script to steal those LAN manager and NetBIOS names to get info from systems and then respond to them, creating an opportunity for shenanigans, an opportunity to catch stuff on the network, which is super useful. But a tool that can come in handy. In terms of man in the middle, or I believe the more common terms these days is becoming on-path attacks, can include a bunch of different things. If you can record traffic, if you are on path, you can play it back later, so you can do a replay attack. If you are between two sources, so if you're between the example we were looking at earlier where there was a NAS and there was a client who was our victim, if you relay the messages between the two, you can read those messages. Potentially you can use that position in order to hijack session tokens. So the many web apps make use of some kind of encrypted token that says, I am this user at this time. And by stealing that token and using it yourself, you can become that person. Similarly, you can fix a session and leave it locked to yours. And if you can get inside of their web browser with a tool like Beef or others, you would, like, for a lot of organizations, all business happens in the web browser. You know, if they're using Microsoft Office 365 and they're using, what else? You got Office 365, you got the Google Sheets, Docs, Drive setup. So being in a position where you are either proxying the browser or you've got JavaScript running that is taking all of the info from the browser and intercepting it, any of those attacks put you in a wonderful position in terms of hacking. But you may say to you, Professor Rosema, there's encryption. You can't see inside of my magical encryption. What could you possibly do to attack that? And what was formerly known as SSL, currently known as TLS, is useful in preventing a lot of those attacks. So you have to figure out ways to work around that. A couple of the ways you can do that is by stripping HTTP off of communications. So I think that's what we're drawing down here. We've got an HTTP connection of some sort, and we are like pretending to the server that, oh, we are the victim, and because we are the victim, this connection to the server appears secure, but to the victim it does not. That's when you take away all the connectivity. And the EFF has a plugin for browsers called HTTPS Everywhere that goes through and defends you from that sort of thing. Available for browsers everywhere. But our friends at the EFF have been offering a browser plugin that would at least raise some alarm bells if you started to connect to the internet and instead found that there were shenanigans afoot and you were trying to connect to an HTTP connection instead. So downgrading back to HTTP is the worst case scenario, I guess. A downgrade attack that downgrades you to a weaker version or one of the old export versions, which I think they're just now retiring, the last of like the 40-bit export strength. They really were SSL protocols back in the day. They're just now retiring all of those. But if you can downgrade somebody to one of those, you were again similarly in business. Windows networks are plagued by the hash attacks, pash the hash, where they don't want you to pass the password around, right? The plain text version of P@SSW0RD. But instead they have you pass a hashed version of that around on the network, which is certainly more secure. However, it means if you see that hash go across the wire because you've got a man in the middle position or because you are you've compromised the workstation and you're running Mimikatz to dump all of the hashes out of the system, then you can pass that along to any of the servers to which you would like to connect, and you will get access to whatever resource is on resource server there. So it's basically as good as having that system's password without having that system's password. And sometimes the thing you do on a resource server is reset a password, although sometimes that can get you tripped up. So we've got a lab for that one too. Bypassing various network access controls is another biggie. So network access controls, usually like 802.1x, I think is the big one. 802.x, is there one in there? Are designed to make you authenticate before you are allowed to do anything on the network. So they want you to authenticate with credentials and credentials for the network that you're on. And if everything works out, you sign in, you are given your credentials for the connection, and then you are assigned to, you start off on like the sign-in only VLAN that allows you to connect solely to the authentication server, and that's it. If your credentials check out, they sign you in then to the appropriate VLAN based on that. The posture assessment tends to be like, are you currently running the latest antivirus kind of stuff? Did your system pass our system checks? If you don't authenticate with those, you will usually wind up in a, like, if say you are a legitimate client but you didn't update your antivirus definitions, they might dump you into a quarantine VLAN where the definitions get updated, and then once that's done, you can re-authenticate and get to the right VLAN. Or, you know, if the credentials are wrong, they might say, you're doing something shady. We're going to put you in the things we don't trust VLAN. If that's the case, there are techniques for VLAN hopping that we talked about that you can potentially try from in there. So obviously, if you're trying to authenticate to the network, you have physical access. So bypassing that, though, it's an exercise left up to the student, usually involving getting your own credentials from someone. I don't know if there have been any like huge vulnerabilities in those authentication protocols. Then once we move sort of all the way up the stack, we're to problems with services. So FTP and TFTP, SMB, SNMP, SMTP, that alphabet soup of file transfer protocol, trivial file transfer protocol, the server message block protocol, or Microsoft's file and print sharing system. Management protocols like the simple network management protocol, which is like up to V3 at this point. And email protocols are sort of scarily insecure, usually, like the simple mail transfer protocol. But you've got others like POP, and really like of that list of all the protocols that are known inside of your system, every one of them has had a problem at some point in history or not. FTP used to be particularly troublesome, although it is in the process of being depreciated for more secure transfer protocols like SFTP or SCP for copying files to and from servers. There were a bunch of problems where you would, like Windows was guilty of this, Linux servers were guilty of this, where you would be able to get outside of the FTP server's assigned directory and into the file system, and then able to download things like the password file and stuff like that, which was bad. So now most systems, even web servers do this, jail the application so that it only works inside of a particular set of folders on the operating system level beyond just the FTP server. If you set these up insecurely, you do like having things like anonymous access with no password is great. Just know that you're setting up what is essentially a web server and that anyone could be able to get into those. I'm not a huge fan of banners. If you've ever taken my Cisco class, you know that I have a challenge out that if anybody can find me case law talking about not having having someone get off of a hacking conviction because there was no service banner, I'm still waiting. I might make that like a $100 challenge. But you can be foolish and put things on your banner that give away information, like thank you for connecting to ftp.blah blah blah dot blah blah blah, the FTP server for the NSA or something like that. Not great. Also vulnerable potentially to brute force cracking attacks. You know, you can spin up a copy of Hydra and throw passwords at them all day, which you say, hey, I've got these lockouts configured where after so many attacks or attempts, we lock either the user account or the IP address. But since you can spoof a lot of those things, potentially you can use that defense mechanism to create a denial of service condition. So if I know that trussell@grcc.edu is the user I want to tamper with, I try to log in with that account a bunch of times, and the next thing you know, trussell@grcc.edu can't log in, and now I've denied service to him. Windows has had all sorts of problems with SMB. The newer ones are, you know, like anything else, more encrypted, more secure, more better, but it's Microsoft. You can only trust them so far. They've had all kinds of problems. They're getting better. I try not to give Microsoft crap. They've basically revolutionized how we secure things. Mail servers, similarly, since they're like internet facing by default, they've been put through the ringer. Oops, mail servers. I was talking about SNMP servers. SNMP was originally not secure at all. Hang on, let me just switch the order. Mail servers, since they face the internet, have to deal with all sorts of issues and have been beat up very, very hard. So like most mail servers these days, if you find a vulnerability in it, it is a surprise just because of how long they've been online and what juicy targets they were. So they've been beat up pretty hard. But they're how mail moves from point A to point B for most of the internet. formerly, I don't know a lot of servers that still do this, that would take a verify string to let you know if you could send email to somebody. So like verify that trussell@grcc.edu is a valid address. Or if you sent a mailing list request, the expand command to it, it would expand back a mailing list, which was, again, all sorts of bad idea. You could use that to amplify attacks against spoofed IP addresses and all sorts of stuff. A verify would let you basically enumerate a, all of the users on a system. And there's all sorts of tools built into Nmap and into Metasploit that will enumerate users on an SMTP server if that's a thing. And then going back to SNMP, the original version, like all of the, I'm pretty sure when the original version rolled out, like a huge swath of network administrators didn't realize they were installing devices that had this protocol running that had a default password of public or a default password of private and would show all sorts of stuff on a network. So if you could crack the community string, which is basically what passed for a password for a long time, you could get in and do anything that SNMP allowed you to do, which for some devices was allowing you to configure a lot of stuff. So those are kind of a bunch of big examples. And let's pause here for reflection and to walk around for a second, and then we'll come back and talk about wireless attacks. That professional